Okay, we're now live and recording. So obviously in 4 or 5 minutes time, you can start whenever. I'm just going to disappear for a little bit.
Thanks, Steve. Hello, everybody. It's time to start this afternoon session. So we have a couple, 5 interesting talks for you to listen to today. And we are going to be starting with the first talk soon. Just to remind you, you can now post anonymous questions on Slack, and you can post all your questions on Slack as well next to the thread of the talk. Instructions on how to post anonymously are in a 3B session on the bottom. You can read how to post this. And so we'll start with Adelie Gorce, who is going to tell us about the improved constraints on reionization from the KSE power spectrum. Take it away, Adelie.
Thank you. Hi, everyone. My name is Adelie. I'm a PhD student at the IAS in Orsay, France, and the Imperial College in London. And I'll be actually moving to McGill in Montreal as a postdoc in October. So I'd like to thank the organizers for giving me the opportunity to talk today about this project I've been working on with my colleagues in Orsay, Strasbourg, and Toulouse. The point of this project, so it's a bit different from what we've heard so far, because it's about CMB data. And so the point was to find a new parameterization of the KZ power spectrum to constrain EOR, and so make a better use of CMB small-scale data. So first, what is the KZ effect? So the KZ effect is when low-energy CMB photons scatter off electrons that have a bulk velocity with respect to the CMB rest frame. And so this results in the photons getting an energy kick, and so adding power to the CMB temperature power spectrum on very small scales. So you have two components. The first one, the one we're interested in now, is the patchy component. So it's when your CMB photons will scatter off electrons in ionized bubbles along the line of sight during reionization. And so the shape of this spectrum is the one, the angular spectrum is the one you see here in the dashed line. It's a bit bumpy. And then there's the homogeneous part of the signal, which is for what happens after the end of reionization. So the way you do at the moment, so sorry, the spectrum here is a bit more flat. It's the continuous one. So the way you use this at the moment with CMB data is that you take these two templates, you look at the amplitude of the spectrum at L equal 3000, multiple 3000, and you adapt this to data. You fit this to data along with other templates. Now to translate in terms of reionization constraint, you take the amplitude at homogeneous time, and then you have scalings that give you the corresponding value for the optical depth, for example. Or if you look at the patchy component of the spectrum, you have scalings that give you the midpoint of reionization and the duration that are illustrated here. So from that, the most recent constraints that have been derived using SPT data and Planck low L data give the first detection of the patchy spectrum, so the spectrum in general, in particular the patchy spectrum. And from this, they derive a constraint on the duration of reionization, where before it was only upper limits, as you can see in this plot here. So there are a few problems with using this method to derive constraints on reionization from CMB data. The first one is that you use templates for the KZ spectrum, even though many works have shown that both the amplitude and shape of the spectrum depend on reionization. And then you also use scalings that are completely dependent on the calibrations they were, the simulations they were calibrated on. So in the end, you have one constraint that gathers very different prescriptions for reionization inside of it. So it's really inconsistent. And to give you an example, so here I have 3 simulations. I'll talk about them a bit later, but which have very different morphologies. And if you use the scalings and the templates, you obtain the 3 dashed line here, so very similar. But if you use the method I'm going to describe in the remaining part of the talk, you get these 3 spectrums. So you lose a lot of information if you only use templates and amplitude at L equal 3000. So how to solve this problem? So we've chosen to go back to the very basic equations that give you the CL, so the power of the spectrum at multiple L for KZ signal. You have a few elements, cosmological parameters, and also these terms, which are going to be directly related to the amplitude of your signal. So the optical depth here, the mean density of free electrons, and the limits of your integral as you integrate over the duration of reionization. And then you have this term here, which is completely going to determine the shape of your spectrum. So it's a bit of a complicated parameter, but you can directly express it in terms of this power spectrum here, which is the power spectrum of free electrons density fluctuations. So we focused on this term, and we've looked at its evolution with time in simulations. So these simulations are the EMMA simulation run by Dominique Aubert in Strasbourg. So the highly resolved radiative hydrodynamics. And so you see this spectrum has originally a very simple structure, flat and then decrease, and then slowly merge into something that looks more like a matter power spectrum. So this early time component, which corresponds to the first half of reionization, is very easy to model. You can just use a power law. So we've chosen that type of structure where you have 2 parameters. You have alpha naught here, which is the amplitude, the constant amplitude on large scales. And it's the maximum value of the amplitude of the spectrum. So then with time, it's going to decrease in amplitude because If at the beginning you just have a few ionized regions, the variance in your field is really high, so the amplitude of the spectrum is high. But then as the field becomes more and more homogeneous, more and more ionized, the amplitude decreases. So that's this alpha naught parameter. And then you have the kappa parameter here, which is the frequency above which your power decreases as a k to the -3. And so similarly, you can have a physical intuition of what it is. If you have no power on smaller scales, it can mean that you don't have ionized regions that are smaller than the corresponding scale. But we'll have a look at this after. So you end up with a very simple parametrization with the power law that then slowly merge into a biased matter power spectrum. You feed this on simulation, you get posteriors for your parameters, you know the reionization history, and so you can completely compute your KZ power spectrum without worrying about limitations such as simulation box size or resolution. So we've applied this to 3 types of simulations to see how robust the description was for different types of physics. So the ALMA simulation I've mentioned before, the RSage simulations that were kindly provided by Jacob Seiler and Anna Hutter. So they're post-processed dark matter fields that include different prescriptions of the dependency of the escape fraction on galaxy properties. And so that translates in different morphologies. And then 21 centimeter fast, you're probably familiar with that we ran for different also galaxy properties. So here are the results. On the upper panels, you have the reionization histories, and on the lower panel, the corresponding patchy KZ power spectra. So for ALMA, you see that if you have two runs with different reionization histories, that translates in spectra that have not only different amplitude as the scalings we used before seem to say, but also different shape. And actually the amplitude at multiple 3000 is the same, which means that limiting yourself to fitting this parameter is definitely not sufficient to describe the whole spectrum. Then for our Sage here, we have very similar reionization histories, but different morphologies. It's the 3 simulations I showed you at the beginning, if you remember. And so it translates into the simulation with the largest bubbles in average, having the largest power, and also peaking at the largest angular scale. So this relates to a fact that's pretty well known, that your spectrum is gonna bump at scales that roughly corresponds to the typical bubble size during reionization. Now, everything's not that simple, because when we look at 21 centimeter fast, where here we have different morphology and very different reionization histories, you find that the simulation that has the largest bubbles actually has the smallest power, the lowest power. So you're gonna have a correlation between all the parameters here. So how can we interpret all of this in terms of the 2 parameters I've defined before? So first, let's look at the kappa parameter. The kappa parameter is the frequency above which your power drops off, as illustrated here. And we find that for all the simulations we have, each time we have larger bubbles, we also have a smaller drop of frequency, a smaller kappa. And that's true at any point during the reionization history. And this is also always related to a bumping scale, so a multiple where your power is maximum, being the smallest one. So larger scale, so smallest multiple. And actually you find a very nice correlation between the 2 parameters that is valid for any simulation, any reionization history, and any value of alpha naught, which means that if you measure the spectrum from data, then you can directly infer the value of kappa, which is in turn related to the bubble size, and so to properties of early galaxies, such as ionization efficiency, etc. Then for alpha naught, so if you remember, it's the amplitude of your spectrum, the maximum amplitude of your spectrum, that's going to decrease with time. It's a bit more complicated, because if we find that a larger variance, a larger alpha naught is always related to larger bubbles. So that's because for a given filling fractions, if you have a few large bubbles, the variance is going to be much higher in your field than if you have a lot of very small regions. So larger bubbles will always going to mean a larger amplitude of your spectrum. However, it's not always going to mean a larger amplitude of the KZ signal itself, because as we've seen for 21 centimeter fast, it's also correlated with the duration of reionization and the midpoint. So you're going to have a strong correlation between your alpha node parameter and reionization parameters, and you need to use other types of data to break this degeneracy. So just as a quick conclusion, this formalism is quick and easy to form a word model. You include a lot of physics with just 2 parameters and the reionization history. And so if you apply it to CMB data, you should be able to get for the first time both the amplitude and shape of the KZ power from the epoch of reionization. And then the parameters also allow you to understand better the physics underlying the KZ signal. You can relate them to, so you can relate features in your spectrum to your parameters and in turn to characteristics in your ionization field, and so to the physics of early galaxies. So that in turn you can combine data from CMB small scales with other types of observations, such as astrophysical observations, tau, or 21 centimeter intensity mapping. Thank you for your attention. If you have questions, I'd be happy to hear them.
Thank you, Adelie. I'm going to, okay, there is already one question from Ken, which says, is it possible to compare your fitted electron power spectrum with other theoretical models, for example, halo model or beta model?
Okay, I'm not sure I really understand the question. So if you mean, so the evolution of the free electrons power spectrum is definitely something we've observed in other types of theories. Just for 21 centimeter, you also follow the evolution of the amplitude with time. It's going to depend at where you're at in the reionization history. And then, yes, so the transition from something that's a bit more power low to a biased matter power spectrum. Some people, you could also argue that it's the 1 term and the 2 term, similar to what you have in the halo, so 1 term halo term, 2 term halo terms, etc. But I haven't pushed the comparison further because the point was really to look for something that was simple and not 2 parameters were enough. So we've stopped there.
So another question, Gareth is telling you, nice talk. One challenge in calculating the patchy KSZ signal is that you need the large scale velocity variations larger than your simulation volume. How did you deal with this?
Yeah, so originally our simulations, because they're pretty highly resolved, they're not very big. They're about 200 megaparsecs on the sides. But the point of using this parametrization is that you can do everything theoretically. So we've looked at bigger boxes to check that the behavior of the, try to go back, that the behavior of the spectrum on very small, large scales was always the same one. So up flat like this. So that works. And then you can just do everything theoretically. So you have the matter power spectrum that you know from your Boltzmann integrator. You have this parametrization that you can extend to whatever scales you're interested in. And so normally you're not limited by the size of your simulation.
All right. Thank you very much. I invite everybody who is talking today to also check after the talk if there are some more follow-up questions and just answer them on Slack.
Thank you.
Right. Thanks, Adelie. So the next talk today is by Yana Khusanova, who is actually not here, but the talk was recorded. So I'm going to try to share it on YouTube. If you guys have trouble hearing it, I invite you to just have a look. The link is on the main conference webpage. But we tested and it should be doable. Okay. Let's see. Okay, I hope you guys can hear this.
Hello everyone, and thank you very much for giving me the opportunity to give this talk. My name is Yana Khusanova, and currently I'm working in Max Planck Institute for Astronomy in Heidelberg. And today I'm going to present the work I've done during my PhD, together with Mathieu Betterman and Olivier Lefebvre and ALPINE collaboration. So the topic of my talk will be the dust hidden star formation rate density at redshifts above 4. And first of all, let's discuss how do we measure star formation rate density. So to measure star formation rate, we need to measure the light from the young and short-lived massive stars. We can measure from the UV light, but since some part of this light is reprocessed by dust, we need to also measure the dust obscured part, which manifests itself in the infrared. And if we know the UV luminosity density and infrared luminosity density, we can easily derive the star formation rate density as a sum of these two contributions and using some conversion factors. However, we don't always have the information about the infrared luminosity, and therefore we can use some dust corrections or emission lines. The easiest way to correct for dust is using the IRX beta relation, where IRX is the ratio of infrared luminosity to UV luminosity, and beta is the UV continuum slope. And this relation works very well in the local universe, where the local galaxies follow the Calzetti attenuation law, but it's very uncertain at high redshifts. We can see from many works that this relation evolves with redshift, and also at high redshift there is a larger scatter of this relation. So what can we do? Ideally, we would like to have the rest frame far infrared data and a good constraints on the infrared luminosity of galaxies, which is a crucial part of constraining the star formation rate density. But unfortunately, up until now, these constraints were very uncertain and the results were inconclusive, since it's quite hard to get a large sample observed in the rest frame far infrared, and therefore the ALPINE survey was built with the goal to get the constraints of this star formation rate density hidden by dust at redshifts above 4. The galaxies were chosen from spectroscopic surveys such as Deimos and Woods, and since all these galaxies have spectroscopic redshifts, we could ensure a high detection rate of C2 luminosity. But since the survey was built in order to get the C2 luminosity, the detection rate of far infrared continuum is lower, but it is still possible to get constraints from the observations of far infrared continuum. And also, this survey is very good to constrain star formation rate density, since it covers a very large range of properties such as stellar masses, FU, magnitudes, and star formation rates. And based on UV data, we can see that these are the galaxies which are on the main sequence. So, what can we do if we have this low detection rate of far infrared continuum? We can use the stacking and derive the average properties of galaxies, even if they are too faint to be detected individually. We combine the galaxies with similar properties, and we can measure the average far infrared flux of these galaxies. To measure the flux, I used the 3 arcsecond aperture to get all the flux from the galaxies, even if there are some maybe small offsets from the phase center, and the uncertainty of the measurements is estimated using the bootstrapping. As you can see on these example images, as we go to higher stellar masses, the far infrared flux is also higher. And this we can use as a proxy for the far infrared flux. How do we determine the infrared luminosity density using these stack images? So first of all, we do the stacks in the bins of stellar masses. We measure the flux on the stacks images, and we can find the correlation between the far infrared flux and the stellar masses. and we need to add to it the information about density. And this we can get from the literature. We can use the Galaxy stellar mass functions to determine the density in each bin, and then we can just convolve these two functions and we can get the infrared luminosity density. And if we extrapolate it to lower and higher stellar masses, we can get the total infrared luminosity density, which can be then converted to star formation rate density. And of course, we can also use other proxies of the far infrared flux. For example, we can use the FUV magnitudes. And the UV luminosity functions we can also get from the literature, since they're quite well constrained in these redshifts. The main caveat here is that using just one point in the rest frame far infrared, we need to get the total infrared luminosity. And for that, it's necessary to use some spectral energy distribution templates. And there are several of them available in the literature, and the results will depend on the template. To choose the templates, I used the stacks of Herschel data available in Matthew Betterman's paper. And I only chose templates which have the reduced chi-square values below 1.5. And from each template, we can calculate the conversion factor from far infrared flux to infrared luminosity. And then if we have a number of templates, we can derive the average conversion factor and the uncertainty on this conversion factor, which can be also propagated to the uncertainty of the star formation rate density measurements. As you can see, we can observe the correlation between infrared luminosity and stellar masses, as well as between infrared luminosity and FUV magnitudes. And this, of course, can be used to constrain the star formation rate density. And these are final results. So I show in the with the orange symbols the constraints of the infrared component of star formation rate density, and in the blue the constraints of the UV component of star formation rate density, and in red the new constraints obtained from ALPINE, with constraints with the mass as a proxy as a star, and constraints with the FU magnitudes as a proxy as hexagons. As you can see, with both proxies, the results are fairly consistent with each other within the error bars. You can see that at redshifts below 3, the infrared component of star formation density is clearly dominating the UV1. And it was expected that at higher redshifts, these two curves will cross eventually. And some works which were attempting to constrain the infrared contribution claimed that already at redshifts above 4, the infrared contribution is negligible, as for example the paper of Koprowski in 2017. But with ALPINE we can see that even if we only use the lower limits, which are shown here as red triangles, still we have a very high contribution from the infrared. And if we extrapolate the results, we can see that there is a very high contribution from the infrared. And if we compare the dust hidden contribution to star formation density with the total star formation density at these redshifts, then we can see that the infrared contributes to at least half of the total star formation density. So to conclude, using the stacks of the targeted sources from ALPINE, I was able to constrain the dust hidden part of star formation density at redshifts above 4 and obtain a very consistent results using the different proxies, and also consistent with other works using ALPINE survey. So we start to obtain a more consistent picture of the evolution of the dust hidden star formation density at redshifts above 4. And we can see that dust still is important at redshifts above 4, and at least 50% of the UV light is absorbed and reprocessed by dust at these redshifts. And if you have any further questions, feel free to contact me.
All right, everybody. I hope you guys have managed to hear this. Let me just try to get out of this. I apologize in my attempts to deal with technical questions, technical issues. I was totally forgot to introduce the speaker. So this was Yana Khusanova that was talking about the dust obscure star formation ray density at redshift above 4 from Alpine survey. She said she might be online. Let me see to possibly answer some questions. It does not look that she's online, but I invite everybody to actually post questions in her thread next to the talk. So since she's not online and she won't be able to answer questions, we are going to move on to the next talk, that's going to be by Laura Sommovigo about worm dust in high-Z galaxies.
Hi, everybody. So I'm going to share my screen. Okay. Do you see it?
Looks great.
Okay.
You can start
so
sharing.
I'm going to start.
Start the presentation.
Okay. So hi, everybody. I'm Laura Sommovigo, and I am a PhD student in Scuola Normale Superiore in Pisa, in Italy, and I work under the supervision of Professor Andrea Ferrara. Today, I would like to discuss about worm dust in high redshift galaxies, its origins and implications. So at this point, I think it's clear to everybody that thanks to the Atacama Large Millimeter Array, in the last few years, it has become possible for the first time to observe the far-infrared emission from high redshift galaxies, unveiling the presence of dust even in these very early stages of galaxy formation. However, many challenges remain open, and some of the reasons are, in my opinion, well summarized in this plot from the paper by Liang 2019. On the left side, you see the spectral energy distribution of a redshift galaxy, which is well sampled by data points on both sides of the gray body-like spectrum, meaning that from SED fitting, one can easily, so to say, infer the dust temperature, dust mass, obscured fraction of star formation, and far-infrared luminosity of this galaxy. However, for the analog at redshift 6 that you see on the right side, ALMA band 6 and 7 only trace the right side of the spectrum, and in general, very few data points are available, just 1 or 2, meaning that it is very difficult to simultaneously infer the dust temperature and the dust mass of these sources. What is done instead is to generally assume the dust temperature, meaning that all the other derived properties of the galaxy are heavily dependent on this difficultly testable assumption. In this sense, SPICA might help us in the following years. This is a proposed new instrument at ESO, and it will have some mid-infrared windows for these high redshift sources. Let me now move to the theoretical part of the talk. So I'm going to describe the dust temperature within giant molecular clouds through semi-analytical models. So why do we want to focus on giant molecular clouds? This is because from simulations from Pallottini 2019 and Behrens 2018, we see that regions which mainly contribute to the far infrared emission of high redshift galaxies are indeed giant molecular clouds, which are the yellow dots in these plots that I'm showing. In our model, we consider uniform molecular cloud in terms of density, star forming with a central stellar cluster. We leave as three parameters: the turbulent velocity within the cloud and the pressure within the cloud. Here is my parameter space for the clouds, and in particular, I would like you to focus on these 2 points. So the blue one should be representative of a Milky Way-like cloud, so a local-like cloud, and its properties are taken from average properties of observed clouds in the local universe. Instead, for the red point, this should be representative of a typical high redshift cloud. In this case, clearly, I don't have any observations to take the properties from, so I get the data for this cloud from simulations. you can see that the high redshift cloud has both larger pressure and larger turbulent velocity, meaning that it survives longer to both supernovae and stellar winds, having a lifetime or dispersal time, which is 4 times longer than the local light cloud. Let me now move on to describe the dust temperature profiles within our clouds. So in this plot, on the y-axis, you have the dust temperature, whereas on the x-axis, you have the distance with respect to the center of the cloud, where I remind you that we have our UV source. So the red line is our high redshift, the dust temperature in our high redshift cloud, while the blue line is the dust temperature in our low redshift cloud. You can see that the high redshift cloud has a hotter dust, and this is mainly due to the fact that this cloud has larger pressure. We can understand this in physical terms because we know that the optical depth scales us the mean square root within our semi-analytical model of the pressure, meaning that the distance at which we reach optical depth equal to unity is much closer with respect to the center of the cloud in the high redshift cloud with respect to the local cloud. So in other words, dust is hotter in the high redshift cloud due to the more compact dust configuration in this structure with respect to the local analog. This is the basic setting of our model. We also include the effect of radiation pressure, and we see that these conclusions do not change. And we find dust temperature as large as 60 Kelvin and above within our high redshift cloud, and luminosity to gas mass ratio of around 10 solar luminosities over solar masses, which is 10 times higher than what observed in local clouds, which is also consistent with what we get for our simulated local cloud. This larger dust temperature has some important implications. When I say larger, I refer with respect to what are the current assumptions on dust temperature at high redshift. And here I'm showing you a plot which on the y-axis has the dust mass, and on the x-axis, the age of the galaxy. So the black curve is the dust production model from Asano 2013. And I would like you to focus on these 2 sets of points, which correspond to the dust mass that Tamura 2019 would need for their observed galaxy, assuming a dust temperature of 40 Kelvin or 50 Kelvin, in order to get the observed far-infrared luminosity of their source. So the point is that if you allow for larger dust temperature, in order to produce the same FIR luminosity, you need less dust mass. In particular, if we consider a slightly larger dust temperature of 60 Kelvin and above, we are perfectly in line with both the Asano model and constraints from supernovae studies, as we only need less than 0.3 solar masses of dust to be produced in each supernovae explosion, and we can allow for some dust destruction during the lifetime of the galaxy. This suggestion is also been met recently by new observation by BACS 2020, which have given a new lower limit for the dust temperature within this galaxy of 80 Kelvin by adding the observed far-infrared flux at 160 micron rest frame. Another implication is related to the IRIX beta relation at high redshift. Allowing for larger dust temperature means that we can reduce the tension between local and high redshift IRIX beta relation. And this is because allowing for larger dust temperature results in larger far-infrared luminosity, shifting the far-infrared faint data points upwards in the IRIX beta plane. However, we have to keep in mind that in our high redshift cloud, the optical depth is very high, meaning that UV is heavily obscured, which is also what was shown in the simulations. So in our scenario, the observable UV radiation should come from stars that have already dispersed the molecular gas around them, so clouds that have already been dispersed. This is in favor of a scenario of spatial segregation between far-infrared emission and UV emission, which should come from spatially separated regions within galaxies. And this is also in line with some recent observations, such as the one by Bowler 2018 and Laporte 2019, which observe a spatial offset between the HST data and the ALMA data, so between the UV emission and the dust continuum emission. This might lead us to question the validity of the IRIX beta relation at high redshift, since this relation assumes the co-spatiality of the 2 emitting regions, so the UV and the far-infrared emitting regions. Finally, I would like to conclude by presenting some preliminary results on a new method that we are developing, which is aimed at constraining the dust temperature using only one continuum observation, which is what we generally have for high redshift galaxy. Here, I'm showing the case of the same galaxy I was discussing before in terms of the dust mass. So the galaxy at redshift 8.31, observed by Bax 2020 and Tamura 2019. For this galaxy, with our method, we get a dust temperature of 83 Kelvin, which is perfectly in line with the lower limit given by Bax 2020. I would like to remind you that Bax's method relies on SCD fitting, so they use 3 continuum data points, whereas we only need 1 by combining it with the C2 line emission. Nevertheless, you can see that we have very large uncertainties on our predicted dust temperature, and this is mainly due to the fact that the metallicity of these galaxies is largely uncertain, and this enters in our methods computation. However, JWST should help us in this sense, since it is expected to reduce the uncertainty on the metallicity of high redshift galaxies. For instance, if we consider a very reasonable reduction down to 30% of relative uncertainty, we reduce the error on our predicted dust temperature, narrowing the range within which the dust temperature can vary between 80 Kelvin and 120 Kelvin. This method has some relevant applications in the context of recent ALMA large programs such as ALPINE and Rebels, which both target C2 emitters at high redshift. I leave you to my summary and thank you for your attention.
Thank you very much, Laura. Please do post your questions. Let me see. So there is a question from Tom. Have you considered variations in dust model size composition? Thanks.
So you mean different grain sizes, right?
Yeah.
Okay, so yes, if I can show you a backup slide I have. So, okay, so here actually I'm showing the dust temperature profile and the density profile that we get, as also including the radiation pressure effect. So it's slightly different with respect to what we see before. And this is because basically the radiation pressure creates a cavity at the center of the cloud and a very dense shell at the boundary of the H2 region. However, the point I would like to show is the second plot, the one that is getting larger right now. So the color bar shows here different grain sizes, which we consider from 0.01 micron up to 1 micron. And you see that depending on the grain size, we have slightly different dust temperature. So before I was showing also always the case of 0.1 micron, which is a typical grain size. But whenever I'm computing the average dust temperature for the cloud, I'm always averaging on the grain size distribution and either on luminosity or dust mass. So I hope I've answered the question.
So I think you did. So here's another question. Maybe I missed the point, but how are you measuring P dust in your simulation, and how this would compare to the fit of MBB to your simulated SCD? And what about the optical depth? Even at lower redshift 2 to 4, when having 10 points of the SCD, TD is not well measured.
So you mean related to the last part, the preliminary result, right?
I'm not entirely sure. I'm just reading the question, but
okay, so I think is related to that. So so basically what we do, I also have a backup slide for this. Okay, so basically what we do is, starting from the usual formula that is used also in SCD fitting, we rewrite the dust mass as a function of the dust gas ratio and the C2 to total gas conversion coefficient, so that we get the dust mass is the product of these two quantities and the C2 luminosity. So at this point, by fitting the single observed data point at 1900 gigahertz or 160 micron, we can get a reasonable prediction on the dust temperature and dust mass. I don't know if this answers to the question, but eventually we can enter in more details in the chat if I have misunderstood.
Yeah, I think it's related to the fact that even at lower redshift, we have sampled a lot of the spectra and fitting the SCD to that spectra gives very uncertain results.
Yeah, but indeed you see that also, I'm going to show again our prediction. I mean, you see that our predictions still have very large uncertainties now. So clearly we can only qualitatively constrain the dust temperature using only one observation, but still it's better than nothing. And without this method, what one does is to simply assume the dust temperature and proceed to compute all the other properties such as dust mass and whatever based on this assumption. So at least we can constrain the region in which one can vary the dust temperature in the initial assumption. Then I don't know if I answered to the question.
Yeah, so there is another question related to that. So maybe you can answer it again in a chat. But another question was, what percentage of the IR luminosities contributed from warmer dust in your model?
Okay, so actually we have, so this is the, okay, so this is the spectra that we get at the beginning of the lifetime of our two clouds. You can see that while for the local cloud, we have a almost perfect gray body. For the high redshift cloud, we have a slightly modified shape. And this is exactly because of the warmer dust, which mainly contributes to this part where you can clearly see that there's a sort of like double peak situation going on. And indeed at shorter wavelengths, we have that the warmer dust, so the one at the peak that I was showing before, is contributing the most. However, when we do we also show two different weightings for our dust temperature. So here I'm showing you the dust temperature, luminosity weighted and mass weighted for our simulated clouds. Especially, I would like you to focus always on the red lines, which are the ones related to the high redshift cloud. You can see that if we think of mass weighting, the dust temperature is really low because most of the dust mass is found in equilibrium with the CMB. Whereas if we consider luminosity weighting, so basically we should be considering the gas which is mainly contributing to the emission, we have larger temperatures. So the one that is mainly contributing to the emission is exactly the warm dust. And we have dust temperature of around 60 Kelvin for our high redshift cloud when we include radiation pressure, and much larger when the radiation pressure is not included, which is the case, for instance, also of the simulations where for spatial resolution reasons, one can not include the effect of radiation pressure. I hope I answered.
Okay, thank you, Laura. There are more questions. Apparently, dust is a very hot topic, so you can answer them on the chat, but we need to move on. Thank you. So the next talk is by Seiji Fujimoto, who is going to talk about the ALPINE-ALMA C2 survey, size of individual star-forming galaxies at redshift 4 to 6, and their extended halo structure.
Okay, so hi everyone, I'm Seiji Fujimoto. I got a PhD at the University of Tokyo last year and now working at the Cosmic Dawn Center in Copenhagen. So sorry, I will turn off the camera due to a potential concern on the internet. So yeah, but yeah, okay. So yes, first of all, thank you organizer for this opportunity. And I would also like to mention that my talk today is one of the outcomes from the large Alpine collaboration, which was only possible owing to the great effort and leadership of our PI, Olivier Lefebvre. So along with my Alpine colleagues' talk and this entire conference, my talk is dedicated to his memory. So now I start. I have a bit updated the title. So today I talk about C2 halo in the early universe. So this illustrates the baryon cycling from the central galaxy to the circumgalactic medium, which is called cesium. So in this baryon cycling, the cesium metal enrichment is very important to understand the feedback mechanism from the central galaxy, which regulates the galaxy formation and evolution. However, if this system is too old and experienced many cycles already, it's hard to distinguish how each pure mechanism contributes to this metal enrichment. So investigating the cesium metal enrichment in the early universe is one of the key proofs to understand the pure feedback mechanism regulating galaxy formation and evolution. So recent arm stacking studies are capturing such earliest environmental pollution in the universe. In our previous study, we performed visibility-based stacking by fully making use of the ALMA archival datasets. The seed line is clearly distributed beyond the dust continuum up to a radius scale of about 10 kilopascal scale, whose decomposed size even extended 5 times more than the rest frame UV emission. So we dubbed this large seed line structure as C2 halo. Hydrodynamical simulation couldn't reproduce such large C2 halo structure, so these results suggest early galaxies eject an amount of carbon-rich gas far exceeding our expectation, and indeed, the C2 halo studies would be a helpful proof to understand the feedback mechanism of early galaxy in conjunction with theoretical studies. One obvious way to go is individual measurement instead of stacking. And another essential work is to understand what powers ionized carbon emission. This is because, the outflow is essential for the cesium metal enrichment, while once after it is enriched, the cause of powering the ionized carbon emission could be a different mechanism like photonization or inflow. So we have these two remaining questions. And now these two questions can be addressed by the ALPINE survey. ALPINE is one of the ALMA large programs in cycle 5 targeting C9 for over 100 main sequence galaxies at redshift around 4 to 6. The successful C9 detection offers us a variety of exciting studies, and in Olivier's paper, we did carefully classify the galaxy into 5 categories based on morphology and kinematics feature based on these large ancillary datasets. So from this classification results, here we select only isolated ALPINE galaxy to remove potential effects on the halo emission from merging galaxies. And we also set some SN threshold to obtain reliable results. There are still remaining 23 ALPINE galaxies. So based on this, we address the first question of the individual C2 halo. By the way, we performed the stacking analysis with this ALPINE sample and confirmed the existence of the extended C2 halo. So it's good to know. But again, what we will address here is individual measurements. So in the studies of extended diffuse emission, the spatial resolution significantly affects the sensitivity. So the left panel shows the left frame UV continuum map taken from HST after smoothing to match the resolution with ALMA. The red contour shows the seed line taken from ALMA, and here shows the radial profile of the surface brightness of the seed line and left frame UV continuum. To obtain quantitative results, we define the intensity of the extended seed emission beyond the smoothed beam size up to a radius of around 10 kilopascal scale, and regard the seed halo as the object whose extended seed emission is detected above 4 sigma level, while the extended UV continuum at the same area is below 3 sigma level. We find that 7 out of 23 isolated ALPINE galaxies are classified as the seed halo object, including these 2 objects. So with the upper limit of the rest frame UV and also with the dust continuum, our previous study already showed that such high seed line ratio over star formation rate at the outer halo area cannot be explained by the low mass faint galaxy. So now we would be able to say that we are identifying the seed halo individually. During these works, we also identify a number of objects whose seed line is not so extended in contrast. We regard those objects without seed halo by setting the 3 sigma upper limit for the extended seed emission and find mostly the same fraction there. When we compare with and without seed halo object on the star formation rate and the stellar mass plane, we find that seed halo objects are generally have the higher star formation rate and stellar mass values. So this difference might be just because the selection bias. So the brighter objects have a brighter outscatter emission, which would be easier to identify. However, we realize that at least 3 seed halo objects have similarly low values on this plane. And indeed, the left panel also shows that, this object might be faint and have larger error bar in the outer halo area, which makes it difficult to identify the seed halo, but still the upper limit of the seed line do not exceed the left frame UV continuum profile. So these results suggest that absence or existence of the C2 halo cannot be explained by the selection bias alone. So studying the difference of the physical property between with and without C2 halo object will enable us to address the second question of what is the origin of the C2 halo. So one clear feature we identified was the velocity offset. So all of our ALPINE targets had deep optical near-field spectra, and here shows the stacked spectra as a representative example. Not only in the stacked spectra, but we also analyze individual spectra, of course, and evaluate the velocity offset of the emission and absorption line features with respect to the C2 line emission. So first, let's see the Lyman alpha velocity offset. The red and blue histogram are the with and without C2 halo object. And the hatched one highlights the C2 halo object whose star formation rate are comparably low to the without C2 halo object. So we find that C2 halo objects generally have the higher Lyman alpha velocity offset, indicating more significant outflow expanding shell taking place in the C2 halo object. But more directly, we also find that higher velocity offset in the less frame UV metal absorption. So remembering this higher star formation rate trend, these results may indicate that C2 halo is related to the star formation driven outflow, which is consistent with the implication from the recent result of the spectrum stacking from much larger sample. Another difference we identified was equivalent width of the Lyman alpha line. So we find that C2 halo objects generally have the lower equivalent width value, indicating that this outflow might be dominated by cold neutral gas, or let's say multi-phase gas mixed with cold and hot, or firstly the hot gas was launched, but it becomes cold at some point through the radiative cooling. As a brief wrap up of this slide, okay, now we are addressing the second question. So the origin of the C2 halo might be the star formation driven outflow, while we cannot rule out the possibility of the selection bias toward the luminosity object. But here I'd like to show some interesting cases well aligned with the star formation driven outflow scenario. So one C2 halo object clearly shows its rotation feature beyond 10 kilopascal scale, and its rotation axis has a good agreement with the less frame UV measure axis. So we performed the realistic 3D rotation modeling. So here the right panel is the best fit momentum one map. And so first of all, we obtain the effective radius of this rotating C2 gas disk is around 4 kiloparsec, which is around 4 times larger than the rest frame UV disk. So we might be witnessing the kinematics of the C2 halo, or let's say a large gas disk co-rotating with the central galaxy disk. So interestingly, when we take a look at the residual map, we identify a symmetric feature perpendicular to the main disk. So this may indicate that we are also witnessing the ongoing outflow, such like the famous picture of M82. The second case is that one C2 halo object also has extended structure in the dust continuum. Since the carbon exists at CGM, it is natural that dust is also there. But once after dust is pushed away from the central galaxy, then it will soon become cold, so which is very difficult to be detected. But the extended dust continuum might be detected in some cases, such as powerful outflow cases. So where the extended dust still keep a good temperature, which we might be witnessing here. So indeed, this C2 and dust halo object has one of the highest Lyman alpha velocity offset and Lyman alpha equivalent with value among the C2 halo object, even with the existence of the large amount of dust. So that strong outflow may help the Lyman alpha escape from this system. So I also touched some implication from the latest model in the last slide. So the recent semi-analytical model calculates the expected C2 emission in the cooling outflow process. In this model, the key parameters are mass loading factor and the circular velocity. And these the best fit parameter will reproduce the 10 kiloparsec scale C2 halo structure. Sorry that it seems that I don't have enough time to fully explain this interesting figure, but likelihood for these two parameters are obtained like this. So if we obtain the kinematics of the C2 halo, we will directly get the circular velocity and easily constrain the mass loading factor at the same time. And this C2 emission in the outflowing phase is also confirmed in the hydrodynamic simulation, including radiative transfer. So this figure shows the time evolution of star formation rate, escaping fraction, and C2 and O3 line luminosity in the hydrodynamic simulation. So we can see that O3 line matches very well with the star formation, while C2 is more continuously emitted relative to the O3 emission, even in the outflowing phase. Where we also see this kind of the anisotropy between C2 and O3. But as the simulation suggests rapid expansion of H2 bubble around massive stars, so the next way to go would be the kinematics of the C2 halo and multi-phase gas structure, which will provide strong constraint on the key mechanism in the feedback. And such ionized gas structure should be addressed with J-based linear spec IFU by targeting the less frame optical line like H alpha and O3. Okay, so at the beginning of my talk, I told you the importance of the CGM enrichment in early universe, and now we are here. So C2 halo is identified statistically and now individually, but it's not always showing some trends. The possible scenario are just selection bias toward luminosity object or star formation driven outflow, but I would like to mention that even in the case the selection bias case, it means that C2 halo is universal picture in early galaxies, so it would be also very interesting. And the next step would be the multi-phase gas structure in 2D plus 3D up to the CGM scale, which will be one of the key proof to understand feedback mechanism in the era of ALMA and J-based. And in the last additional slide, I would like to mention how fruitful outcomes we have from Alpine survey owing to Olivier's great efforts and leadership. Also, I focus on the extended halo emission in my talk, but my paper also addresses the individual size and spatial offsets between UV and C2. So if you are interested on those papers, please take a look on archive. Okay, so that's it. Happy to answer questions.
Thank you, Seiji. We all miss Olivier for sure. We have very few, we just have a minute for a question.
Sorry for that, yeah.
There is a question. Thanks for the very interesting talk. Do you see outflow signature in stacked UV spectra, blue shifted absorption line, or of C2 halo objects?
We identified the blue shifted absorption line feature not only in the stacked spectra but the individual spectra. So this figure shows the individual basis measurements. So yeah, that histogram shows the C2 halo object, and the blue shade is without C2 halo object, and we identify that more blue. So C2 halo object has more blue shifted absorption line features.
Okay, there is another question. If you can detect dust in the outskirts of the galaxy, it could imply that the dust grains are not destroyed there, right?
Yes, yeah. So in this case, we identify very extended dust up to similar scale. So dust grains are not destroyed there. Yeah, I think so.
Okay. Thank you very much. We need to move on, unfortunately. No worries. There will be more questions, just answer them on Slack. Our next speaker is Shotaro Kikuchihara about, I probably mispronounce, Shotaro Kikuchihara. I can. He is going to tell you how his last name is pronounced. Who is going to tell you about extended Lyman alpha halos around redshift 2 to 7 Lyman alpha emitters investigated by intensity mapping technique.
Okay, thank you for introduction. Can everyone hear my voice?
Yeah, we can hear you.
And can you see my screen?
Not yet.
Not yet? Okay. Sorry. Now can you see it?
Yeah, we can see your presentation.
So now, let me start my presentation. And hello everyone, my name is Shotaro Kikuchihara. I know my name is a little bit wrong to pronounce, and the true pronunciation is Shotaro. And I am a PhD student at the University of Tokyo. And today I will talk about the extended Line-alpha halos around higher redshift Line-alpha emitters investigated by the technique what's called intensity mapping. Okay, now let me start with the introduction. Okay, this figure shows the schematic view of the circumgalactic medium and the intergalactic medium around galaxies. And you know, Line-alpha halos are created by the scattered Line-alpha photons inside the circumgalactic mediums. And the Line-alpha halos are found ubiquitously around star-forming galaxies and more extended than UV continuum. For example, in Stylo et al. 2011, they observed the redshift 2.65 Lyman break galaxies, and they find the Lyman-alpha emissions are more extended than UV continuum, as illustrated with this figure, or shown in this radial profile. Lyman-alpha emitters here and UV continuum in this here. And Matsuda et al. 2012, they observed redshift 3 Lyman-alpha emitters. This shows the snapshots. And they derive the surface brightness radial profile, and they go down. They go down to the 10 to the minus 20th order of the surface brightness. So here's the question: and the how largely extended are the Lyman-alpha halos? And also the origin or the evolution of the halos are still yet to be understood enough. So we want to answer these questions, but here's one technical difficulties of the detection limit. So in order to resolve these difficulties in our analysis, we focus on two things. The first one is what's called intensity mapping technique. I remember this topic is already touched in the yesterday's talks. For example, in Croft et al. 2018, they took cross-correlation between the position of the ratio of 2 to 3 quasars and the Lyman-alpha emissions traced by the fiber spectra. And what's good about taking cross-correlation is thanks to this, they successfully removed the systematics from foreground and background sources. And finally, they reached down surface brightness down to the 10 to the minus first order. So in our analysis, we also use this analysis. And the second thing, we make advantage of the deep and wide images of the Subaru hypersupreme cam. And in our analysis, we utilize the data from two large surveys. One is the cosmic hydrogen reionization unveiled with Subaru Chorus. And the second one is the Hypersupreme Can Subaru Strategic Program, HSC-SSP. And here there are 4 narrow bands we use and 5 broad bands, and whose throughputs are represented with these curves. And there are 4 narrow bands, and each trace the ratio 2.2, 3.3, 5.7, and 6.6 Lyman-alpha emitters, respectively. And in our analysis, we first begin with the analysis on the UD cosmos field, which is as wide as 2 degrees squares wide, corresponding to more than 10 times the size of the full moon. Okay, and the next, we use the Lyman-alpha selection, but we utilize Lyman-alpha catalog, which is constructed by the Noito in prep. So here I briefly shows what they will do and what they done here. They first detect the sources with using sex structure, and next they carried out the machine learning and visual inspection onto the detected sources. They use the convolution neural network, and they classify real Lyman-alpha emitters and remove the spurious sources, and they finally constructed the final catalog. These two figures shows the snapshots and the positional distributions of the selected Lyman-alpha emitters. And the number of the finally selected Lyman-alpha emitters are listed here, in total as many as the 2,000 Lyman-alpha emitters. Okay, next, let me explain more detail what the intensity mapping is. Our goal is to derive the Lyman-alpha surface brightness, which is schematic is here. So first we took the cross correlation between the position of the Lyman-alpha emitters and the Lyman-alpha intensity, which is traced by the narrowband images. In this calculation, we took the mean of the pixel value inside annuli at distant r from the central line alpha mirrors. However, taking this cross correlation is not enough because this result includes not only line alpha emission, but also the PSF and the sky background. So we have to subtract the contributions from this PSF and sky as a systematics. So in order to evaluate that, we took cross correlation between the position of the foreground sources and the line alpha intensity. And this result yield the surface brightness from these two contributors. And we select the foreground sources so that the magnitude and the FWHM distributions are matched to that of the line alpha emitters. And subtracting this systematics from the total surface brightness, we finally derive the line alpha surface brightness like here. Okay, so now we adapt this analysis to our samples and finally obtaining these results. This result shows the surface brightness profile versus the radius at the redshift 2.2, 3.3, 5.7, and 6.6. And you can see at these 4 redshifts, our data points reach to the order of the 100 physical kiloparsec size. And in order to test our results are valid, we compare our result to the previous work. This figure compares our result at the redshift 5.7 to the previous results from the Leclerc et al. 2017, who detect the line alpha emitters at the Hubble ultra deep fields with VLT muse. And in order to do a fair comparison, we constructed the subsample whose line alpha luminosity is at this range to match the line alpha luminosity of this object. And you can see that our profiles are smoothly connected to the inner disk profile around these regions. So to sum up our results, we find the line alpha halos extended up to the order of the 100 physical kiloparsecs at this redshifts, and outer profiles here are consistent with the extrapolation from the inner profiles if we match the line alpha luminosity. Okay, now let me go to the discussion part. First, let's look at the evolution of the halo profiles. This figure compares the profiles at these 3 redshifts, and the field symbols shows our results, and the open symbols shows the Leclerc et al.'s results from the Muse Hubble ultra deep field. And to do fair comparison, all of these samples are constructed so that the line alpha luminosity are in this range. And you can please look around here, and you cannot see a significant evolution from redshift 6.6 to 3.3. However, next, please look at this figure. This figure shows the same as the left one, but corrected for the cosmological dimming effect with this order to match the redshift 5.7. And we plotted our result at the redshift 3.3 to 5.7. And here you can see that there is a possible decreasing trend from redshifts at redshift 6 to 3. And the next discussion is a comparison to the simulation at the reionization epoch. In this figure, we plot our result at the redshift 5.7 here, and we compare to the simulation result of the Chen et al. 2011, who carried out the line alpha radiative transfer and the hydrodynamic cosmological simulation at the similar redshift. And this dashed line shows the contributions from the resonant scattering in the circumgalactic medium, which is illustrated like this. And this dotted line shows the contributions from the satellite galaxies, which are around the central galaxies, the line alpha emitters. And this solid black curve shows the sum of these two. And you can see our result prefers the scenario A, the resonance scattering. And we did the same test for the brighter subsamples, whose luminosity is in this region. But even in this case, our observational results underestimate the model, so the conclusion. Okay, now this is a summary. We select the 2000 llama emitters at this redshift using Subaru HSC images and the machine learning technique. We detect the llama halos with intensity mapping technique, and finding the halos are extending up to the 100 physical kiloparsecs at high redshift. And we find the possible decreasing trend of the profiles if we corrected for a cosmological dimming effect. And finally, we compare our results to the simulation, that's redshift 6, and our observational results agree with the resonance scattering in the circumgalactic medium. In the future, we will investigate the origin of the halos in more detail with intensity mapping or other lines such as Balmer alpha or O3. Okay, this is the end of my talk. Thank you very much.
Thank you very much, Shotaro. Are there questions? So while people ask questions, I have one. People write questions, sorry. I have one. One of the things is you're basically selecting your sample based on Lyman alpha luminosity. And are you worried that the sample might be biased? And wouldn't it be easier, not easier, but wouldn't it be better to basically do cuts based on, say, stellar masses or something similar?
Your question is about when constructing this kind of subsamples?
Yeah, so your subsample is limited by luminosity on Lyman alpha. And right. I'm worried that at redshift 6, you are sampling a very different population than at redshift 2 while doing this cut.
But when I compared to the low redshift, we matched the Lyman alpha luminosity. So I think in this case we did a comparison. But are you worried about the difference of the halo mass or something between the low redshift?
I wonder if cutting by stellar mass would be a better and more physical way to compare the two samples.
I think that's another way, and that's the thing we haven't done yet. But yeah, I think that's the next thing we have to investigate.
Okay, so there is another question by Matt. Nice results. You prefer resonance scattering instead of local satellites, but how would your profile look in the case of halo gas that is fluorescing because of the ultraviolet background?
Is that question is about the recognizing between the fluorescent scenario?
Yeah, so how would fluorescent scenario make this plot different?
I think the with the current data set, I'm not sure if fluorescent scenario how largely the fluorescent scenario affect this result. I think comparing with the other lines are also necessary to discuss about that. But I think that's the important point to discuss when about the origin. So now please let me discuss at the Slack channel.
Okay. So another question is, have you estimated the incidence of AGN in the 2000 redshift 2 to 7 LAE sample?
We haven't yet checked how many AGNs in our samples, but yes, the making the cross matching to X-ray catalog or something, and investing in similar things, will be important. Yes. But currently no. That's the next step. Yeah.
All right, so we need to move on. Thank you very much.
Thank you, everyone.
And so we are moving to our last talk, which is by Gareth Jones on kinematics of redshift 4.4 to 5.9 galaxies in ALPINE.
All right. Can you see full screen?
I cannot see full screen.
All right, well, we did test this before, but it seems to not want to work today. So you can see mostly full screen now.
Yeah.
Okay, so I guess I'll get started then. Yeah, so I'm Gareth Jones, a postdoc from the University of Cambridge. And today I'm pretty excited to be able to tell you about our work in the ALPINE collaboration, looking at kinematics of galaxies within the first gigayear of the universe. So my author list here is a little bit small, but really the ALPINE collaboration is pretty huge. This is a list of all of the co-authors and authors on the current set of papers. And we're currently spanning 11 countries. So I just want to point out that all this work is due to everyone's work. So you've already heard from Yoshi yesterday and Yana and Seiji today, but just to reiterate, ALPINE is an ALMA large program looking at 118 star-forming main sequence galaxies between redshift 4 and 6, looking at C2 and rest frame far infrared continuum emission. And there's a whole bunch of science that we can do since these are in the cosmos in the good south field. But we're just going to focus on the kinematics of the C2 for now. So C2 kinematics can include a whole host of different physical properties and processes. Seiji's already gone over the spatial evidence for outflows. Michele Genofi looked at the spectral stacking of C2 profiles and found evidence for outflows in the spectra. We can also look at mergers as something that's related to kinematics. Michele also looked at a double merger that shows evidence for a very large diffuse halo surrounding it, where I looked at a triple merger at redshift 4.6. But mainly what I'm going to focus on today is rotation and dispersion, where this is just an example of velocity field and velocity dispersion field. But I also want to point out that Mirko Dessois-Zavadsky looked at dynamical masses, compared them to gas masses. So first I'm going to look at the work done in the survey description paper by Olivier, where we tried to do a morphokinematic classification. So Seiji showed this figure before, but just to kind of describe it in more detail, a group of 8 of us looked at a set of diagnostic plots, tried to classify each galaxy into one of 5 classes. And these diagnostic plots contain C2 channel maps, the wideband photometry in different bands. And then along the bottom here, we have moment 0 integrated intensity plots with continuum overlays and velocity fields, position velocity diagrams along the major and minor axes, and spectra. So by looking at these diagnostic plots for all of our galaxies, we tried to classify them as a rotator, which is a single galaxy with a nice ordered velocity field, a merger where there's multiple components, or a single component with a really messed up velocity field, dispersion dominated, where we have a definite source with no evident velocity evolution, either extended and resolved or compact and unresolved, or just too weak to tell. So the first cut that we did was we took our 118 galaxies that we observed, and Matthew Retherman ran a line search algorithm and found that only 75 of these galaxies were detected at more than 3.5 sigma in C2 emission. So we did this analysis for those 75. We found a really nice kinematic diversity, but we found that 12 of these galaxies were too weak to classify, mostly because these lines were very broad and we didn't have enough signal to noise in each channel to do kinematic analysis. So if we remove these 12, we're left with 63 galaxies. We find that roughly half of them are mergers, a quarter are extended resolved dispersion dominated, and the remaining quarter are pretty evenly split between rotators and compact unresolved dispersion dominated. So again, these are for galaxies between redshift 4 and 6. So this sort of kinematic diversity, where it's not all mergers and it's not all well-ordered rotators, is kind of nice. You might be surprised that there's any rotators at all around redshift 5, but the fact is that we see rotators pretty much anywhere we look. So of course, local galaxies, we have amazing observations in very high numbers. So this is an example from the Wisdom survey, where the resolving beam is to the lower left. We resolve the disk. It's definitely a well-ordered rotator. At intermediate redshifts, the KMOS 3D and the XIN CC-SINF surveys found evidence for a whole bunch of rotating disks using H-alpha. And if we move out to higher redshifts, all the way up to redshift 8.3, we find evidence for rotating galaxies, mainly from the detection of a well-ordered velocity gradient. So yeah, ALPINE is 4.4 to 5.9, so finding disks in this redshift range is not ludicrous. So what we tried to do next was to analyze the rotation of these galaxies by fitting tilted ring models. So this is a mosaic done by Michele Genolfi of the 75 galaxies that were detected in C2. And so we took each of these data cubes and ran them through the search algorithm at 3D Barolo to see which sources had strong enough emission to actually fit with models. And of these 75, we found that 26 were actually strong enough. And these are ordered in decreasing signal to noise. So we detect the strongest signal to noise and one low signal to noise source that happens to be merging with a strong serendipitous source. So yeah, this is the moment 0 or the integrated intensity. If we look at the velocity field at the moment 1, we see really nice kinematic diversity, some well-ordered rotators, some really complex mergers, and then some just obvious noise, essentially. Since these are data cubes, we can also look at the velocity dispersion maps, where again, we see some central velocity dispersion peaks, some peaks on the side. So yeah, in order to quantify this, we then fit each data cube with a tilted ring model. So we took the entire data cube and fit it with a model, which is much better than just taking the velocity field and fitting it with a model, because we can look at the data, the model, and the residual in multiple ways. So the first way is we can look at the integrated intensity, or the moment 0, for the data cube, the model cube, and the difference between the two, the residual. We can do the same for the velocity field, the velocity dispersion field, the position velocity diagram, which is a slice through the cube taken along the major axis here and the minor axis, where the contours are the model and the color is the data. And then we can also look at the spectra for the data, model, and residual. And this is actually the example shown by Seiji in a couple talks ago. And so you can see that evidence for an outflow there. So this sort of shows that we can see how well 3D Barolo is fitting these really simple ring models to each data cube. And we can also see where it deviates, because we don't expect these galaxies to all be perfectly flat, thin, rotating disks. We expect them to be surrounded by mergers and gaseous filaments at these redshifts based on comparisons to simulations. So in addition to looking at single galaxies, we can try and add on more evidence to the kinematic classifications that were done in the paper by Olivier. So we can say that some galaxies are very well fit by these tilted ring models with small residuals and very well fit spectra, pretty much perfect position velocity diagram fits. Some are fit with very low velocity gradients, but very high velocity dispersions. So these are dispersion dominated for sure. And then there are some galaxies that are just terribly fit with a tilted ring model because they are not rotating disks, they're actually mergers. So we can add on this evidence to the initial qualitative analysis. And a paper by Michael Romano and Paulo Casada will be coming out in the next few months looking at this sort of analysis in a more case-by-case basis. So I'd just like to point out that there are now 15 papers out in the Alpine collaboration, covering a whole bunch of different science cases. And if you're strapped for time and only want to read 3, I want to point you to Lefebvre, Betherman, and Feist, just looking at the 3 survey overview papers. But if you're interested in mergers, dust attenuation, IRX beta, luminosity functions, there are a lot of really interesting science cases. So just to conclude here, Alpine is a really exciting kinematic playground, essentially. From the kinematic classification, we find a really nice diversity of sources. From an initial 3D Barolo model fitting, we see some are good rotators, some are good mergers, some are just dispersion dominated. But there's still a lot of work to be done. And then finally, with the rest of my Alpine collaborators, I'd like to remember Olivier Lefebvre and his dedication to this project, and I'd like to dedicate this talk to him. So thank you.
Thank you, Gareth. All right, please post questions if you have any. I actually have one. So as you push this to higher and higher redshift, it's more difficult to distinguish between rotators and say mergers because you don't really always resolve things, especially in the imaging. So how well do you think you can do that at your highest redshift end, and what kind of resolution do you need to push this to even higher redshift?
It's a good question and a pretty large concern right now. Yeah, so these are only around 6 kiloparsec per beam. And so what we're finding is that we don't have the resolution to actually tell these rotators and mergers apart, even if they're only a few kiloparsecs separated. And so we don't have, there's definitely no chance of getting close separation mergers. But we do have high resolution 0.1 or 0.2 arcsecond observations coming up soon. So hopefully that should be good enough. But yeah, that's definitely a problem, and yeah, higher resolutions needed.
And do you think high resolution is going to be sufficient? I mean, are you still going to be able to detect those objects? Because obviously with high resolution, you get the fluxes are harder to detect, right?
Right. So yeah, these are all main sequence, and I guess one of the best comparisons is this work by Marcel Neilman. This is a 0.2 arcsecond observation of a main sequence galaxy, and I think they were able to detect it. It did take a long time from what I remember though. This is ALMA C2. So yeah, instead of 30 minutes, it's going to take 10 hours per source, but it is possible.
Okay. So I don't really see any other questions on the thread. I would invite everybody to post some. It's always a problem with the last speaker on, on the agenda. People are eager to take lunch if you're in Europe, for example. So I'm going to close this session. I'm going to invite everybody back at 1:30 UTC, or basically in 2 hours, wherever you are now, for the next session. So sessions 4A and 4B are happening today, don't forget that. Meanwhile, please do post some questions for Gareth, and hope everybody's enjoying the conference. Thank you very much.